Howdy stranger, welcome to the fourth and final part of this video series. This time we will do a whole bunch of improvements to the game, mostly on the graphics side of things, but first we'll add the last missing parts like the HUD elements. Let's get right to it. The first thing we'll add to the HUD is the speedometer. It appears to be made up of three different elements: the background, the transparent bar, and the solid bar. All three are set up as sprites, so they should be quite easy to get working as we already have code to draw sprites in the HUD. We'll remove these calls to add prim and replace them with calls to our render sprite function. The first try is a fail, so let's take a closer look. Let's change the position values to take the first set in the array, as that's most likely correct since our screen scaling is based on the lower resolution of 320 by 240. Let's see if that helps. Nope. Still nothing showing up, so let's check again. Well, we're only drawing the bars, but not the background for the speedometer, so let's add a call to draw that and try one more time. Still no speedometer on the screen. What's going on here? We know our sprite drawing code works because there are other sprites in the main menu which work just fine, so the problem has to lie somewhere else. Here we go. This loop will move all three sprites to some other position on the screen, so let's comment it out and run the game yet again. Finally we see it, and the bars are even filling up as we accelerate. It's a good start, but it doesn't look right because the red bar is supposed to be semi-transparent. Checking the code which sets up the sprite data, we can see that the blue color of one sprite is set to a constant called red_TRANSL, which I assume stands for red translucent. We can check that constant in our sprite drawing code to change the alpha channel from fully opaque to transparent, so let's do that. The red bar is still fully opaque, so that apparently didn't work for some reason. Oh, it's because blending is not enabled for these sprites, so we'll check the same constant in the blue color channel to enable blending, and that should do it. The missing pixels on the bottom right of the speedometer are not a bug in our code, that's actually what the asset looks like on the PC version. Nice, that looks good. Let's move on. Right after the speedometer code, we have a function called addTime, which we have not adjusted yet, so let's have a look. It has several calls to add prim, which we can simply replace with a call to our render sprite function. Add text and add number we already covered, so we'll skip those. The next function we haven't looked at yet is called addDelEnd, and it's the same deal here, just replace the sprite rendering call with our own. After that we have set car textures, but it doesn't look like we need to do anything there. The same goes for the text data function. Now we get to update race HUD, which contains quite a lot of code, but nothing which needs adjusting. We'll also ignore this calc position function, but after that we get to screen footer, which actually has a call to add prim, which of course we would normally replace with a call to render sprite, except this time the primitive is not actually a sprite, so that won't work. Let's run the game and see what the HUD looks like at this point. There's a lap record time on the left, but it seems a bit misplaced. We'll fix that in a bit. Okay, so this primitive is of type FT4, a textured flat shaded quad, which we've seen before. We'll just drop in the usual code to draw a quad and hope it works. After that we have center text, which already works, so we can just scroll past that to display lives. Actually, before we do that, let's get rid of the frame rate counter and take a quick look at addTime again. It's multiplying the X and Y positions of the sprite by the upres variable, which we don't need, so let's just comment those lines out. Nice. The lap record numbers are now in the correct position on the screen. This code will also eventually draw the current lap times at the bottom left of the screen, but we'll only see those in a little while. On second glance, we also have the same upres multiplication in addDelEnd, so let's get rid of that. Alright, now finally back to display lives. This one should be fairly simple, as we just have to replace the addPrim call and fix the positioning code to use the same position as the speedometer as a reference. A quick test shows the lives being drawn as stars on top of the speedometer, and every time you restart you lose a life. Good stuff, moving on. Next up in the HUD we have the function display win-lose, which will draw a picture of the driver you picked on the screen at the end of a race. It's another textured quad, so we'll add some of the usual code here to draw it. This drawing code should really be refactored into a function which can just take in a primitive of type ft4 instead of repeating the same code multiple times for each case, but we're here to move fast and get things done, not to write beautiful code. Following that, we have a function called backpoly, which draws a semi-transparent untextured black quad that fills the screen. When a race ends, the game keeps rendering the track and the ships in the background, which gets darkened by this backpoly layer to make the images and text on top of it a bit more readable. We'll just write our own code here to draw a black quad with alpha set to 0.5, which fills the entire screen. As there isn't really more information about the original color and alpha values, we can easily discern from the original code. Taking a quick glance at the rest of the HUD code, it seems the next two functions are just showing some text when you win a championship, one for the Venom class and another for the Rapier class. There's nothing to adjust here, so we'll keep scrolling down. We also have a function called initTrackText, which seems to load some kind of texture and sets up a bunch of magic values, but it doesn't look like we need to touch it. Finally, we have display race info as well as draw HUD, which just contain calls to all these functions we already adjusted, so it looks like we might be done with the HUD code. A few adjustments have to be made here as we copied and pasted this code from somewhere else where the width variable was just called W instead of width.
3, 2, 1, go!
Now we can see the lap times at the bottom left of the screen, and we'll just skip to the end of the race to check if everything there looks good. It appears to have crashed whilst doing a mem copy for the pilot image. This seems to be copying pixel data into some direct draw pointer, so we'll simply comment all of that out and test again.
3, 2, 1, go!
This time we see the race end screen more or less as expected, but the whole thing is too dark. It seems we're drawing the backpoly too late, after we've already drawn the picture of the racer and all the text. It's also crashing at the point where we can write our initials into the high scores list, this time due to a variable being used without being initialized. Indeed, the compiler is right this time, and when we commented out the upres calculation we forgot to actually set the values for new x and new y. With that fixed, let's see where the backpoly function is called and move that code up to before the display win-lose function is called. Once again, I'll just skip to the end of the race here. Alright, that looks a lot better, even though the congratulations text is still behind the screen darkening polygon. This could be fixed by moving the backpoly call to happen even earlier, but it's good enough for me. You may have noticed that the outside view of the shield power-up doesn't look very good. There were also a few overlapping polygons on the ships that were flickering due to some sea fighting. There doesn't seem to be anything wrong with the shield handling code, so the problem must lie elsewhere. The only other option is that this is all caused by not culling the back faces of the polygons as they are rendered, so let's quickly fix that. We enable culling in our renderer at the beginning of each frame, and then it looks like we only have two calls to set GL enable cull in the game code. Only one of those is setting it to false, so we'll just change it to true and take another look at the game. The shield now looks good, and nothing else looks broken, so I guess we can safely leave backface culling on permanently. We have a few extra animated objects in the game which we haven't looked at yet, so let's do that, starting with the so-called start boom. We have a function which iterates over all the objects and counts all the ones which have names that begin with the word start, whilst adding them to a list. It's very similar to the function which counts the stadiums for the crowd sound handling. We have the exact same type of thing for objects called red light, as well as some object the developers decided to name donkey in the code. Okie dokie then. These must also be used somewhere in the code, so let's find out where, starting with the red light, which seems to be updated here in color red light. The function appears to do exactly what it says, changing the value of the red color channel by a sine wave. I suppose this would make the object appear to be blinking in the game, but since we just loaded it once as a VBO, we will need to update it before it does that in our version. As there's only one object of this type, we can just create a variable to store its object index so we know which object to update. We'll do this in the initRedLight function, which on second glance should probably return once it finds the object it's looking for, but we won't change it as we don't want to change the original game's behavior. quick test shows no change because there's no red light on this track, only tracks 8 and 11, so we'll take a look at it a bit later. First, let's deal with the so-called start boom, of which there are at most 4 on any given track. We'll do the same thing here, where we'll store the IDs of the objects in a variable, and then we'll just call createGLObjectBuffer with those IDs whenever they get updated. During editing, I noticed this call should have gone inside the for loop above it, as only the last object gets updated here, which should only be an issue whenever you restart a race from the pause menu.
3, 2,
This time the semaphore lights up in sync with the announcer counting down the race start. Let's see if we can spot the red light object. I don't exactly know what I'm looking out for, so I've decided to change the landscape object's loading code to only load in the one with red in the name. Well, there it is, although the light doesn't appear to be blinking. I checked the PlayStation version and it doesn't blink there either, so I guess it's fine. Next up we have the so-called donkey object, which according to the code should rotate back and forth along the x-axis. It's only present in the Arredos 4 track, so let's take a look to see it. Since the code is changing the rotation matrix for the object, it should already be moving without us having to do any extra work. Well, there it is and it's rotating, but not in the way it's supposed to. The name donkey here is referring to a nodding donkey, also known as a pump jack, which is a pump for an oil well. The issue here seems to be a matrix multiplication ordering issue, so let's change that in our renderer. Instead of setting up the rotation matrix and then translating it, let's set up an identity matrix, translate that, and finally rotate it by multiplying it with the rotation matrix. Now that looks like it's supposed to, and with some luck we may have also just fixed some other rotation issues which we hadn't even noticed yet. That's it for the animated objects. Let's move on. At some point it became clear that something is broken with the weapon particles, as over time the amount would decrease until there were no visible particles being emitted at all. With no real clues as to why that's happening, we need to figure out the issue first. To help debug this, we'll use the framerate display code as our base and use it to show some numbers about the weapons and particle effects instead of the framerate value. We'll run a couple of loops here every frame, which will count the number of active weapons, which will be shown in the top row, then the number of active particles in the second row, and the number of particles with a negative count value, which are particles which should be emitted after a delay. The negative count value indicates how many frames that particle will wait until it's shown and is used for the explosion effects. A positive value indicates the lifetime of the particle. Ugh, the numbers are too big and overlap each other. Let's bring their size down a bit. Okay, that's better. Now we can see that as we activate the shield, the number of active weapons goes up to 1. We should expect that over time these values go back down to 0, however explosions seem to cause the bottom row value to grow over time and it never decreases. That gives us a pretty good clue about the fact that something is wrong in the second loop inside the add effects function which is handling the explosions. Let's see here. Here it is. The explosion particles are added with a random negative value for the count variable, but it's being calculated as a signed car and then set to negative. There's a chance here that some of these come out with a negative value which is then set to negative again, resulting in a positive value when they should always be negative. Changing this cast to an unsigned car should fix the issue. Let's apply the same fix inside update effects, as a value of -6 here means that the count variable should get a positive random value as its lifetime, thus making the particle visible.
2, 1, go!
Alright, the debug values now behave as expected, so now the particle effects should be working as intended. There's a couple of things to note here though. First of all, the colors of the particles are not quite right. They don't look anything like they did in the original game, and when for instance a rocket or missile is fired, the active particle count shoots up to 140, which is the maximum number of particles, and only drops back down after the explosion. Let's improve the colors of each effect by changing our color table values. I still don't know what the original values were, so here are the values I got through trial and error, which at least somewhat match what the PlayStation version did. Now the smoke trails look good, but for some reason the explosions are always green. First of all, let's crank up the maximum number of particles from 140 up to 1400. Then let's change the amount emitted during an explosion from 30 up to 300. Increasing them by a factor of 10 should make it so that explosions look a lot more powerful, while still leaving room to have multiple projectiles in flight simultaneously without ever filling up the array. Yep, that certainly is a lot more particles. Now for the green explosions. It appears the color is never set correctly from our new color table for the explosion sprites, so changing that should fix it. There we go. That looks a lot more like fire now than it did before. Maybe increasing the number of particles per explosion by tenfold was a bit much, but I like it, so I'm leaving it like this. The debug code showing the weapon and particle counts can also be removed now, as everything here works as expected. A nice and easy effect we can add is some distance fog. We can do this by calculating the distance to the camera in our vertex shader and passing that value over to the fragment shader. Let's call this value depth, and then write a new function in our 3D fragment shaders which will calculate the amount of fog based on the depth of the current pixel relative to the near and far planes. Then we simply use the fog value to set the alpha of each fragment before it's drawn. The effect is subtle, but it works, so let's also add it to the untextured 3D primitive shader. In order for this to work correctly, we have to enable blending when drawing anything 3D in the game, most importantly the track and the surrounding landscape objects. The reason to add this is simple. The original game had a very low draw distance, so things which were far away were never visible to the player, but now, since we render the entire track and all the landscape objects every frame, you can see sections of the track which look strange as they're just hovering in the air far away in the distance. This effect will also make it so that there's no harsh line at the far plane of the camera projection where you can see stuff pop in as you move forward. Instead, there will be a smooth transition towards transparent, which means that at the horizon, everything should blend towards the color of the sky dome behind it. To demonstrate the effect better, we can just change the near and far plane values in the shader to be much smaller than what our actual projection matrix values are and run the game. Ignore the few visible artifacts, as those are caused by only changing these values in the textured primitives fragment shader without also changing the colored primitives one accordingly. I think you get the gist of it. Moving on. So far the game has only been playable with a keyboard, but it's not the true Wipeout experience unless you are playing on a gamepad. We'll add that to our SDL input by once again having a mapping, but this time from joystick buttons to bit shifts in a bit field called joystick register. The mapping I'm showing here is for an Xbox controller, which feels slightly wrong to play a PlayStation game with, but it is what it is. The SDL code to handle joysticks and gamepads is pretty well documented already, so I won't discuss it here beyond quickly showing how it looks. Most of this is very similar stuff to what we did with the keyboard handling, except the joystick axes have to be stored in a variable called etcjoy1 so that we get analog steering. Including the control.h header alone does not work, so we also have to include object.h, track.h, ships.h, and weapon.h. Okay, this doesn't quite work yet. It turns out with the latest version of SDL you have to get the IDs for the joysticks before you can call SDL Open Joystick. With that fixed, the buttons are working fine in the menu, and in-game everything is fine except for the ship constantly turning to the left. This took a short while to debug, but in the end I managed to track down where the etcjoy1 variable is used to set another variable called neg1.twist, which was defined as a car when it should have been an unsigned car. Now the gamepad controls work as expected, so we can move on to the next thing. So far when we've run the game, all the textured polygons have had a bilinear filter applied to them. I'm not a fan of this, but it's nice to leave the option there in case someone wants to have it. In the graphics options menu in the game, we have a possibility to change that, except that our renderer doesn't care about the value right now. It looks like the game stores the setting in a variable simply called ft, which presumably stands for filter textures. Let's bring it into our renderer and change the condition in loadgl texture to also check for that. We already pass in a boolean value to prevent filtering UI stuff like the text, so we can just check for that as well as the ft variable in the condition. Now when we launch the game, we have nice and crispy unfiltered textures everywhere. Let's go to the options menu and change the setting to make sure it's working properly. Yep, when we turn the texture filtering on and launch the game, it's immediately visible that all the textures are filtered in all their blurry magnificence. Since we're already here, we might as well adjust some other stuff in the graphics options menu. Let's deal with the screen size next. The previous handling has been commented out by someone else before we got here, but we'll bring it back and make it switch between windowed, exclusive full screen and borderless full screen modes. We'll disable the option to toggle the sky on and off, as that seems pretty much useless. We'll change the highest resolution option to display the current screen resolution just for fun, even if the option doesn't do anything. Now we'll change the strings for the screen size option to display what that option actually does now, and add a call to our SDL set window mode function whenever the option is changed. Let's quickly test it. It appears to have crashed because we corrupted the stack around the screen string variable. I guess 8 characters aren't enough to hold the strings we're trying to put in there, so let's increase it to 11. Now it doesn't crash, but we have the screen size and texture filter options on top of one another. Let's adjust these values here to fix that and check again. Almost. Now the actual setting values are still overlapping, so let's fix that. Well then, the text isn't aligned properly, and the resolution value just shows 0x0. The screen size options are also not really working as intended for some reason, and they also show 0x0 for the full screen option. Alright then, let's sort this out. First of all, the x-coordinate for the screen size option is at 190 pixels instead of 180 like the other options. For the resolution string, I would expect that once again 8 characters is not enough, so we'll bump that up to 9. Well, the text is now aligned nicely, but otherwise nothing else has improved. Strangely, changing the resolution is also breaking the textures on the ship which rotates in the background. Let's increase the number of characters in the resolution and screen size strings to 12 just to be absolutely sure that's not the issue. It's not. Alright then, let's try fixing the resolution string first. I suppose these variables are never set to anything reasonable once we've created the window, so let's add a few lines of code to SDL window to do that. Well, that's also failing, so let's get the error from SDL and figure out why. It says invalid display. Fair enough. When I first wrote this code, SDL3 didn't even exist, so all of this window handling code was written for SDL2. Let's go ahead and get the display index first, and then use that to get the display resolution. Alright, that works. Let's fix the code below to also do the same. Alright, well the text for the full screen option is still not working correctly, but at least it is switching to full screen as intended. I can't show it here because the screen capture stops when I pick that option, so you're just gonna have to take my word for it. Another thing we should do is to add handling for the case when the window gets resized. We'll add it to our SDL event polling and SDL input and have it refresh the window resolution as well as the projection matrix in the renderer. Now resizing the window works well enough, but it's crashing in the graphics options menu because the resolution string is once again corrupting the stack. Well, first of all, we were using the wrong constant for the screen size here, as both full and small are defined as 0, which meant that we were overwriting the text in this array with the wrong text. Let's fix that and try again. Oh yeah, the stack corruption is still happening. That's probably because the resolution is too big to fit into the character array, so we'll once again resize it, this time to 12 characters, just to be sure. Finally, that all seems to look good, but changing the resolution value, even though it shouldn't have any effect at the moment, is breaking the textures somehow. It appears that changing the resolution calls this change screen function, which we've halfway commented out already, but it also contains a call to restore textures, which is likely the culprit. Let's comment out the call to change screen and test. That seems to be fixed. The only thing missing now is making the borderless full screen option work correctly. The SDL set window bordered call will return true on success, so this condition is wrong. Fixing that fixed the behavior, and now we can successfully switch to the borderless full screen mode. When the game starts, it should play a video before we get to the title screen. This intro video is just a regular MPEG file, so let's make a player for that. We'll grab a simple MPEG decoder library from GitHub called PLMPEG, which coincidentally is made by Phobos Lab, the same guy who made the Wipeout rewrite project. The whole thing is just one header and is nice and simple to use. Good stuff, shout out to Phobos Lab. After adding the header to our third-party includes folder, we'll create a header and CPP file pair called glmoviePlayer. Then we'll add two functions, one to start playing a file and another to update the player. We'll need to add a define here for PL MPEG implementation before we include the PL MPEG header, and then we can get straight to business by writing the vertex and fragment shaders our player will use. There's nothing too interesting about the vertex shader except what we do with the vertex positioned here, as we just want a full screen quad to render our video into, but we don't want to mess around with any matrices for this. Then we have the fragment shader, which will need to do some fun stuff to convert from the YC RCB color space to RGB. It'll use a matrix, which we can just hard code with these values here to do the conversion. This setup comes from the example code which comes with the PL MPEG library. The rest of the shader just grabs each color channel value from a set of 3 textures and combines them into a color, which then gets multiplied by the matrix. Next up, we define a bunch of variables for the player to use, and we'll also forward declare a few internal functions here to update the video and audio, as well as for creating an OpenGL texture. We'll also add a function to clean up once we're done, and we'll start by filling that out. It doesn't really do anything surprising, just destroys the PLM movie decoder, the audio device, gets rid of the shaders and textures, and finally the vertex buffer and vertex array objects. Now on to the function which plays the video file. We'll call PLM create with file name to load the video, check to make sure that worked, and then we can get the audio sample rate as well as the video dimensions from PLM. We'll set callbacks to decode both the video and audio, and then set options to not loop the video, enable audio, and set the audio stream to the first one in the file. If the file contains an audio stream, we will use SDL to play our audio, so we'll call SDL open audio device to do that. We'll also set a constant for the number of audio samples we will buffer at any given time, so that we can set the audio lead time in the PLM decoder, as this will help to synchronize the video and audio playback. Next, we create a vertex array and vertex buffer for OpenGL and use the init shaders function from our renderer to set up the shader program. Then we set up the vertex and texture coordinate vertex attributes and create the textures. The function which creates the textures is just standard OpenGL stuff, nothing special here. We'll create a helper function which updates a texture with one data plane from PLM, and then we can use that in our update video callback to update all 3 textures with the image data for that frame of video. We'll also have to update the audio stream and the update audio callback, but after looking over the SDL3 documentation, it turns out we don't actually need to use SDL open audio device, but instead we will use SDL open audio device stream. Now we can just call SDL put audio stream data and give it the data coming from the MPEG decoder. To finish up, we will implement the update function, which will be called from the game. This will call our poll SDL input function, so we can skip the video by pressing a key or gamepad button, and it will also check if the window has been closed to clean up the video player. Now we have to calculate the time elapsed since the last update, and use that to call PLM decode. Once the video playback has ended, we call our cleanup function and return, otherwise we will draw the current video frame. Standard OpenGL calls go here to bind and clear our frame buffer, set the viewport dimensions, etc. Then we do some simple math to calculate the vertices such that we make the video centered in the game window and scaled up in a way that maintains the original video's aspect ratio. Find the textures, find the vertex array and buffer, find the shader program, and draw the 2 triangles that make up our quad before swapping the window. Back on the game side of the code, we have a commented out call to MPEG anim in the doInit function, which we'll bring back, and then we'll replace the call to shell movie start with our own playgl MPEG movie. Following that is a while loop where we will add a call to keep updating our movie player until it's finished. The original code was taking the path for the movie directory from a variable called movie_dir_base, which was originally pulled from the Windows registry, but we don't want that, as every path should just be relative to the game executable, so we'll just remove all those calls and keep those paths empty. On first try, the code would add 2 / before the video file name, so we'll also comment out that code and try again. This time it's failing in the init shaders call, but at a glance the shader code looks alright, so let's debug that to see what's wrong. Alright, the fragment shader fails to compile because apparently a global type sampler requires version 400 or later. Global type sampler? No, we just want the regular 2D type here, so let's fix that in the shader code. Finally, the intro movie is playing, and even the sound is working as intended. That's pretty good, but it would be nice to be able to skip the video, so let's quickly add that possibility. We'll have to add a few includes from the game as well as this crazy bit of code to handle the input, and then we should be able to use the getMenuKey function to check for inputs the same way the game code does. We'll add a few buttons to skip the video, as well as the left and right buttons to jump forward and backward in the video, just because we can. Including the control H file also requires a few other includes, as we've already seen earlier, so we do that and then test. It seems we are immediately exiting the video player because one of the get menu key calls is saying that either the start, back or select button is pressed even when it isn't. After a bunch of debugging, I figured out the cause is the value of this neg1.head variable, so as a shameless and disgusting hack, I just set its value to FF when we start playing the video, and that seems to have fixed it. I also found this awesome video on YouTube called Wipeout Intro Cinematic Remake from someone named Benjamin Brosdau. I apologize if I'm butchering the pronunciation of your name, and decided to grab a copy for my personal version of the game. Since the rest of the game now runs in high resolution, the original intro cinematic looks a bit out of place, and his version is fantastic and even available in 1440p. Link to his video is in the description below. The game doesn't use any real-time lighting, but at some point it occurred to me that it does have lighting baked in as vertex colors for the track. We can see this by removing the texture color entirely from our shader output and running the game. If we load up, for instance, the Aridos 4 track, we can see a brownish hue on all of the track sections which are in direct sunlight, which then turns to a bluish gray when inside a tunnel. Let's try using these colors to simulate an ambient lighting factor when rendering the ships. We'll introduce a new uniform in both our 3D textured and colored fragment shaders, and we'll add it as a parameter to our drawing functions in the renderer. We'll also define a default color of full white for cases where we don't want the ambient lighting to affect the rendering. In the drawing functions, we can check if an ambient color has been passed in. If it has, we hand it along to the shader, otherwise we simply use the white color. Now in our ship rendering, we need to figure out what is the color of the track underneath the ship. To do this, we'll get the pointer to the first face of the track section nearest to the ship, which should already be available as it's used to check if the ship is going over a weapon or speed up pad. The first face in the track section is the left bank, so we skip that and go to the next face, which is the left half of the track surface. We can then check if the ship attributes contain the flag L side, which means it's on the left side of the track, and if not, we will skip to the next face, which is the right side of the track surface. Now we just need to pass this pointer to the track face struct over to the drawing function. The drawing function must be updated as well, first to take in the face pointer and then pass it along to our object rendering function. That function receives the same update to take in the face pointer and then takes the ambient color from the face color values. The color values are defined as cars, so we'll quickly change them to unsigned cars to make sure we don't get negative color values. Finally, we just add our ambient color to every call which renders a primitive and make sure we pass null when rendering the sky. That does it for the ships, but we also have to adjust any other calls we have to those primitive rendering functions, simply passing null as the ambient color value. There's quite a few of these, so an alternate strategy would have been to create custom functions just for the ship rendering and possibly even another set of shaders for them, but this is good enough to test out the idea and see how it looks. Personally, I think it's pretty cool. If I were working on this more seriously, there are a few adjustments I would make. First of all, the flames at the back of the ship should not be affected by the ambient color as they get way too dark inside the tunnels. Second, the effect is quite drastic, especially when flying over a speed up pad or weapon pad, as the ship color is heavily affected by that. To improve it, I would probably add a bit more code to the shader to give some control over how much the ambient light color affects the base color of the ship, instead of just multiplying it directly. Additionally, I might try to set it so that the speed up and weapon pads only influence the bottom of the ship by checking the normals of the triangles being lit. The game uses this constant here called time constant with a value of 33 to calculate whether it needs to update the game logic by calling race control. Even though we get a pretty high frame rate, the game only updates once every 33 milliseconds, so about 30 times per second, and it's hard-coded to do that. That means that at 60 frames per second, we are actually seeing the same image for 2 frames before it updates. Changing that value to something lower like 16 milliseconds will make the game update twice as often, but as a consequence it also runs twice as fast. Since all the game logic is based on integer values, there's no easy way to change this. If we try to have it run twice as fast, but only move objects half as far, we would end up changing the behavior of the game. Imagine something gets a value of 3 added to it every update 30 times per second. If we want to do the same thing 60 times per second, we would have to add half of 3, which we can't represent as an integer, so we would either have to add 1 in one frame and 2 in the next, which would probably make for some jittery motion, or we would have to change almost all of the game logic to use floating point values, which could be scaled by a delta value per frame, but that too would likely change some of the game behavior. Luckily, we can do something a bit better, which is to let the game logic update every 33 milliseconds and then use interpolation to get the positions and rotations of things for the frames in between updates. This is going to require some changes to the way we render things in the game, so to that effect, let's start by enumerating the 3 types of rotation transforms used by the game. We'll call the first one regular and the other 2 HPR and RPH, which stand for heading pitch roll and roll pitch heading respectively. You see, the game uses 3 different ways to calculate the rotation matrix for the camera and the 3D objects. If we look for set skeleton direction, we can find all 3 of them. If we look inside these functions, we see the math being used to create the matrix. Let's compare them to the classical rotation matrices we would expect to have in any math library. I've gone ahead and written out all of them next to each other to make them easier to compare. CGLM does exactly what the Wikipedia article calls the extrinsic version. The first version in the game, which we'll call regular, is pretty close to that, but not quite the same. Even though the trigonometry is the same, some of the signs are different. The HPR and RPH versions are even more different.
What the fuck is this?
After staring at this for longer than I would like to admit, I just gave up on trying to understand them. It turns out that's not necessary for what we want to do here. Alright, so back in our renderer, we will add a define which will let us switch the interpolation on and off just to make sure we haven't broken anything in the process. Now we will add another enum for the types of things we will be interpolating, namely the camera, the ships, the weapons, and the droid. Next we will have to have a value for the interpolation fraction which we can set from the outside. I'm calling it interpolation delta here as it's linked to the delta time, although there's probably a more appropriate name for it. We will also need a function to store an object's transform. We'll need to know the type of object and the type of transform to use. We'll have an index value for the ships and weapons, followed by the heading, pitch, roll, and position values for X, Y, and Z. Then we'll need a method to set the model matrix for these objects, as well as 2 methods to update the view matrix, one for the sky where the camera's position is static, and another one for everything else. To implement these functions, we're going to need some structs which will store our transform data. One which just stores the transform itself, and another which will store the transform type as well as the transform data. Let's start by dealing with the camera first. Interpolation happens between 2 values, so we will store both the current frame transform as well as the one from the previous frame. Now we can fill out the setGLTransform function to store the transform for the camera. When interpolation is enabled, we save the old transform into the previous camera transform variable, and then we can start updating the values in our current one. Since we're taking the raw values coming from the game, we will convert them into values we can use at this point. To do this, we will need a new helper function which will convert an angle from the game, which is in the range of 0 to 4096 for a full 360 degree circle, into a floating point value in radians, so between 0 and 2 times pi. For the position values, we simply divide the value by 4096. We'll skip the function to set the model matrix for now, as that's not needed to get the camera working. Before we can fill this out, we're going to need 3 separate functions to deal with the different types of rotation matrices. We'll call the first one createGL matrix, and it will correspond to set skeleton direction, doing exactly the same trigonometry, but this time using slightly more accurate floating point values. We pre-calculate the sine and cosine values for the 3 rotation values, and then put them into the first 3 columns and rows of our 4x4 matrix, making sure that we're matching the old game code. Following that, we have a fun hack which took me a while to figure out, but the second and third column values all have to be negated, but only for the camera. I don't know why this is the case, as the game code does not do this, but this was the only way I could get this to work correctly. At the end, we can just translate the rotation matrix and copy it to the destination matrix. It's done this way so that these functions can be used for either the view or model matrix without having to repeat it. Alright, now we do the same thing for the HPR and RPH versions of this code, matching the trigonometry in the setSkeletonDirection HPR and setSkeletonDirection RPH functions of the game. Most of this is pretty much the same as the first function, except that in the HPR version, we have to set the position values directly into the bottom row of the matrix instead of translating it after the fact. Again, I have no idea why, as I'm not that good at math, nor do I care enough to figure this all out beyond just getting it to work. Once we have all 3 of those functions, we can finish our update camera matrix function to take the camera transform values from our cache and call the function corresponding to the type of transform being used by the game. In case interpolation is active, we will lerp between the previous transform values and the current ones. The static version of the camera update, which is used to draw the sky, is the same as the regular one, except the position is always at 0 on all 3 axes. Okay, this should be enough for the render. Let's look at camera.cpp to find all the places where it calls set skeleton position or one of the set skeleton direction variants, so we can cache the updated values in our renderer. The camera code seems to use both the regular and RPH type of transforms. With that done, we have to calculate the interpolation ratio, which we'll do in ayrace.cpp inside the main race loop. We'll also slightly improve the game's time calculation here, as it's calling how long at the beginning and at the end of each frame, but really it only needs to be called once. When setting the interpolation delta value, we check the control choice value to make sure the game is not paused to prevent the camera from shaking between the previous and current camera positions. We can actually move the 3 createGL matrix function declarations out of the header, as they're only being used internally by the renderer. Now we have to go to every place in the game code where the view matrix was being set and remove those calls, otherwise they would overwrite our interpolated camera. I'm also hoping that we won't have to set the view matrix multiple times in the game code, but just once before we render the sky, and again right after that for all the rest. Let's try it out. Immediately it crashes due to a division by 0, as both the frame duration and the remainder values were 6. That's fine, we can actually remove the subtraction by the remainder here, as the duration value should be accurate enough now. Well, the game runs now, but the ships are nowhere to be found. The motion is also no smoother than before, it's still only updating 30 times per second. Let's fix the missing stuff first. In some places, when we set the model and view matrices, we actually move the camera instead of the model matrix, so let's fix those places and test again. Now everything is being rendered as before, so at least our matrix functions seem to be working fine, but the frame rate is still not improved. After debugging for a bit, I tracked it down to the check for whether the game is paused. The condition should be checking if control choice is -1 and not 1. With that fixed, we see a nice and smooth camera motion, but the ships and droid are very jittery as their positions are not yet being interpolated. Let's do that next. We'll store the transforms for all of the ships. The number of ships in the game is defined as 8, so that's how many transforms we'll need for those. We can already create similar arrays for the weapons, of which we'll need 20 because that's the maximum number of active weapons in the game, and we'll also need one for the droid. Before we draw the ships, we have to tell the renderer to set the correct model matrix for each ship using the new function, and we'll remove the call to the old setGL matrix model function. Now we need to store the transforms for the ships after they've been updated, so we'll do that here immediately after the call to race control. The droid is also updated in race control, so we can also store its updated transform in the same place, and we can replace the old matrix code for the droid with our new calls right before we draw it. Now the ships and droid have disappeared from the game, which is to be expected as we haven't implemented the new setGL model transform function yet. This will look similar to the new camera update functions, except it will take different transforms depending on the object type. After we have all our transform values, we call the createGL matrix function corresponding to the type of transform that object uses, except this time it will update the model matrix instead of the view.
3, 2, 1, go!
Now the ships move smoothly, but the droid is still missing. We'll deal with that later. Let's quickly implement the weapon transforms first. Over in weapons.cpp, we once again look for all the skeleton updates and add our own code to cache the transforms in our renderer. For this, we will add a variable which holds the index of the current weapon being updated, as that's not a value we have inside the individual weapon update functions. For some reason, the weapons contain values for heading and pitch, but no roll. That's fine, we'll just use whatever was being passed into the set skeleton direction functions and go with that. With those done, we can now move on to the shadows cast by the ships. Those were also jittering quite a lot, so we'll need to implement interpolation for them, except that they're not objects like everything else so far. We'll add a couple of functions just to handle the shadows in our renderer, one to store a position and another to actually draw it. Each shadow contains 6 vertices, so that's what we will cache. Storing the data, we'll just use a simple memcopy to copy the vertex data, and to draw the shadows we will move some of the drawing code into the renderer and adjust it slightly. We'll also add a new function which will update the shadow vertex positions, as that needs to be separate from the drawing. It will use the same code as before, except this time we will already convert the vertex position values to floats and pass them over to the renderer. On the drawing side, we can get rid of almost everything except for the UV coordinate conversion, which is needed to draw the shadows correctly. Now we just need to add a call to update the shadow transforms, and since the shadow positions are tied to the ship positions, we'll do that in the same place where we update the ship and droid transforms. While we're at it, let's also move this call to Aurora Borealis to the same place so that it happens at a consistent 30 times per second. Last but not least, we have the particle effects, which should be nice and easy to deal with, as each of them just requires a single point in 3D space as its transform data. We'll apply a similar treatment to them as the shadows, where we create custom functions in the renderer to store their positions and to draw them. Now we can add a call to store the effect position in the update effects function, and to draw them, we will move the code which creates the actual vertices over to the renderer. And that should do it. Let's run the game and see what we've got. Alright, the droid is still missing, the shadows have the wrong opacity, and some of the particle effects are spawning in the wrong places. The shadow is easy to fix. We just accidentally put 1 instead of 0.5 for the alpha value when adjusting the drawing code. For the effects, I suppose we should already set their positions in the add effects function whenever new particles are added. At first glance the effects look alright, but there was a strange glitch in the camera motion at one point and the shield is wobbling back and forth like it just drank a dozen cans of Red Bull. The shield is still using the old call to set GL matrix model, so that would explain why its position is not being interpolated correctly. In fact, all the weapons were still being drawn with the old model matrix code, so let's change that and test. Hold on, what is this droid doing here phasing in and out of existence? There was a copy-paste error when we load the object transforms. We were reading a weapon position instead of the droid one here. Now the droid looks good.
3, 2, 1, go!
The ship and shadow were all moving smoothly, but the particles and camera are still occasionally exhibiting some weird behavior and the shield is not drawn at all. It looks like we forgot to store the shield's transform in the update shield function, which explains why it was missing in action. So let's add that and make sure we didn't miss any other weapons either. Okay, let's take another look. The shield is fixed, now to deal with the particles. It occurred to me that the particles get reused once they have expired, so we may be interpolating between their previous position and their new one. That should be pretty easy to fix. We'll just add a parameter to differentiate between the first time setting that particle's position and any subsequent updates. If it's the first time, we will change the code to store the new position in both the current and previous position caches. Whilst doing that, I also realized that we are currently just doing a linear interpolation for the positions as well as the angles of our camera and objects. That works fine for positions, but you should never do a naive lerp for angles, as at some point they will wrap around, and if you don't handle that case, your interpolation will actually move backwards. I think that's what's happening with the camera, as it always seems to glitch at the same points in the track, probably because the rotation value is wrapping from a high value back down to 0. We'll fix this by implementing our own lerp angle function, which specifically handles that case. It's pretty simple, so I don't think I have to explain it. Let's just replace all the angle lerping calls with this and see if it works. Okie dokie, there we have it. I think pretty much everything works quite well now, and the game feels much better to play than the original version ever did. This marks the end of this series, but I'll leave you with a few things I would still add if I were doing this as a commercial project. First of all, I would obviously go over all the code again and clean up a lot of stuff. Whilst this is all in somewhat working order, it could definitely be better, and there are probably still more than a few bugs in there. I also think supporting the assets from the PlayStation version would actually be nicer than the ones from the ATI 3D Rage version. The speedometer would look better, and the ship liveries look different in the PC version. I think I prefer the look of the PlayStation ones. There are also some high-resolution texture packs which are supported by a few emulators. I think supporting those would be a no-brainer in a project like this. The droid used to have cool lighting on it, but sadly this version of the code only has a commented out call to the function which did that, and the code itself is nowhere to be found. It could be a fun challenge to try and reverse engineer the original PlayStation version to figure out how it worked. The ambient lighting trick needs some adjusting as I mentioned earlier, and should also apply to the weapons and particle effects. It may even be worth interpolating between the colors of nearby track faces depending on the distance to them. On the audio side, it would be cool to implement true 3D positional audio for surround sound setups. Finally, some post-processing could be nice as well. I've played around with a few ideas in this codebase, mainly adding some anti-aliasing as well as a radial blur which blurs the edges of the screen and increases as the ship speeds up. I guess I might as well add here that if anyone at Sony ever sees this, I would love to do an official remaster of this game and its sequels for modern consoles, so by all means get in touch and send me a dev kit. Alright, that does it for me. Holler at me in the comments if you have any questions and I'll try my best to answer. I'm also planning on making more series of this kind about other games, so if you have any requests or suggestions, feel free to leave those in the comments section. Thank you so much for watching. I really hope you enjoyed it as much as I did making these. With that, I say goodbye and see you on the next one. Later!